Welcome to Gauss Law. We learn about Gauss Law, the net flux and electric flux. So when we talk about Gauss Law, we say that it rates the electric field. It rates the electric field at a point on a closed Gaussian surface. Gaussian surface with the net charge enclosed by the surface. So this is what we call Gauss's law, and of course we have to understand what we call the Gaussian surface. There's what we call Gaussian surface from our definition. So the Gaussian surface, when we talk about this one, we say this is simply a three-dimensional space through which flux of a vector is calculated. So that is what is termed as a Gaussian surface. So let us briefly have a look on electric flux. Electric flux, for you to understand the concept of electric flux, we simply think of a number of field lines. So here we have to talk about the field lines. So we think about the number of field lines piercing a unit area of a surface, and the other number, the higher the electric flux. So the electric flux denoted by this, which is found by that is electric field times change in the area. That is how we find the electric flux. And lastly, let us have a brief look on the net flux. So when we talk about a net flux, to find the net flux through the surface, we find the flux at every surface. We find the flux at every surface. Then we sum out the results. Then we sum. And that is all about Gaussian law, net flux and electric flux. So we simply take an example. For example, our example here says the shown figure. This is our figure, our diagram we have here. It is x equals to 3 meters, and here x equals to 1 meter. This is a cube. The equation says the shown figure shows an uniform electric field given by the electric field, that is 3.0 xi plus 4.0 j, pierces a Gaussian surface cube. That is E, that is the electric field, is in newtons per coulomb. Find the electric flux through the right, left, and the top faces. Solution. So of course we can be able to start from the right face. Let us be able to start from the right face. We know that the electric field is given by 3.0 xi from our equation plus 4.0 j, and of course we know that the electric flux is obtained by the integral of the electric field times the change in the area. That is how we find the electric flux. Therefore, change in the area changes direction. That is, change in the area changes direction. So let us now insert the electric flux will be able to be obtained by the electric field. That is our equation is here. So we just insert it here, 3.0 xi plus 4.0 j times the change in the area, and of course times I. Let us now multiply inside. This is simply this one. So let us now multiply. So in multiplying this, we obtain the integral of 3.0 xi, change in the area I, plus 4.0 j, change in the area, times the I. So you can be able to know that j times I is 0. So this part becomes 0, and therefore what we'll be able to obtain here, we simply obtain the integral of 3.0 x times the change in the area, because I times I is now 1. So this one is 3 is now a constant, 3.0 is a constant, and then we remain with x times the change in the area. And of course, we know that x is also a constant, so it is 3.0 x. Integral of change in area, it is simply the area. So our x, in the first case to the right, our x is 3, so it is 3.0, and then of course times 3, and change in area, we obtain 9.0 a. So the area, we can be able to know that the area we have here, x, we have x is equal to 3 and x equals to 1. So we simply say 3 minus 1, that is 2, and we know that the sides of a cube, if this is 2, that is 3 minus 1, we obtain 2. This is 2, the sides of the cube are equal. This is 2, 2, 2, so the area is simply 4, that is 2 times 2. 9 into 2 squared, it is 4, so we obtain 36 newtons meter square per column. That is through the right face. Let us go to the left face. Let us obtain the area of the left face, the flux through the left face. So we repeat the procedure for right face. However, two factors change here. The element change in the area points to the negative direction, thus change in area will be equal to negative change in area because of the negative direction. And on the left face, x is equal to 1.0. So with the changes, we find flux through the left surface as follows. In repeating the procedure, we obtain that change in area is equal to negative change in, that is the area of course. So this means 3x times the integral of change in area. This will be given by 3 times the value of x is 1, and then of course times the area, which is negative 3 because of the left side, there is a negative here, and then times change in area, 2 times 2 is 4. This gives us negative 12 Newton meter square per column. And lastly, let us obtain our area of the top face. So we know that in the top face now, change in the area will be given by change in the area times of course j. Then our flux will be equal to the integral. We have our equation 3.0 xi plus 4.0 j, and of course times change in the area times j, and therefore we obtain our flux as this the flux as 3.0, that is the integral of 3.0 x times change in the area times I times j, then plus 4.0 change in the area times j dot j. So this is giving us 0, that is the integral of 0, plus 4.0 times change in the area, which is giving us 4 times change in the area, which is simply 4 times 2 squared, which gives us 16 Newton per meter times meter square per column. Thank you so much for watching. Please subscribe to this channel.